All right, let's go ahead and get started. So welcome to our second and I guess final Zoom session. Remember, provided I don't all of a sudden take a turn for the worse and get more sick again, we're going to start meeting in person beginning tomorrow. So before we get started here on today's material, I kind of wanted to go over one thing that might be useful for you in preparing for Friday's exams. Remember, we have our first midterm exam on Friday. And essentially, it's just going to be a long quiz. So it's going to be like a quiz that's at least twice as long as the one that I gave you on the first week of class. And the questions will be relatively similar. So they'll ask you to kind of explain things or say whether things are true or false. And then once we get to chapter 4, you also have to prove a few things as well, which we'll begin talking about today. Now, studying for exams in a course like this and also your future math courses when you get to the higher level courses in the math major will be a bit different from the way you studied for your exams back in calculus 1 through 3 and differential equations. So for those classes, what you did was you did the homework, you went to class, did all the normal things. And then for preparing, you mostly just focused on doing problems. So you did maybe went over the homework problems again, or you did problems from previous year's exams, where you went to an online textbook or the internet and found problems to do. And that worked well enough. And that's one of the best ways to study for math, of course, is to practice. And for this course, that's still going to be true. So I'd still recommend that you make sure you finish the homework for chapters 1, 2, and 4 before the exam here, and make sure you do as many problems as you can. But one additional thing that I would try to do for this course and also for your future math courses is I would try to, at the very least in your head, but also on paper as well, preferably, make some sort of like framework or outline for what we've talked about. Make some kind of summary saying all of the different big picture topics that we've hit on and what all of the main ideas for the class are, because that's what higher level mathematical courses focus on more, not so much specific problems, more so than ideas. So make sure you, at least mentally, if not on paper, summarize all of the main ideas that we've covered so far in chapters 1, 2. And by the way, the exam will be primarily on chapters 2 and 4 because we didn't have a quiz on those, though there still could be some chapter 1 materials. But just take that into account. Make sure you at least mentally summarize everything that we've done so far in the course. And that's just as helpful in this class as is doing problems. I also recommend. All right, so any questions on that before we get started on the material for today? Questions on studying or class in general? All right, well, let's go ahead and get started on the material then. So today we're going to finish up chapter 2 and we're going to start chapter 4. So chapter 2, remember the whole idea here is we're learning about logic. And of course, we are logical beings. We know what that is intuitively, but it's also good to explicitly state a lot of the things that we take for granted. And 2.10 is the last big section of this chapter. 2.10 is we're talking about the negation of certain statements. So oftentimes in mathematics, you may want to find out what a statement does not mean, or the negation of a statement. So an example of that, and probably the most common example of this, is suppose that you have the statement P implies Q, like this. And you may want to prove this statement is true. You may want to prove that whenever P is true, Q will be true as well. But sometimes it's easier to prove this statement if you consider it in the contrapositive, which remember the contrapositive is where we flip the order of the implication and we negate both of the statements. So P implying Q is the same thing as not Q implying not P. These are logically equivalent, as we discussed yesterday. It doesn't matter what the statements P and Q are, is going to be true for any of them. So sometimes it may be easier to prove this statement right here as opposed to its equivalent statement right here. So in order to figure out what this is even saying, you need to find the negations of P and Q right here. So what this section is going to do is we're going to practice finding the negations of certain mathematical statements, both in terms of the English language and in terms of symbols. Let's go ahead and begin by negating and or statements. So and or are very common words in mathematical statements. So we want to understand how to negate those. And last class, we actually learned the two primary techniques of negating these, which are called De Morgan's laws. De Morgan's laws essentially tell you that the negation of an and is an or, and vice versa. So remember, the first form of De Morgan's laws is not P and Q is the same thing as not P or not Q. And we also have the version of De Morgan's laws where we negate P or Q, and that's logically equivalent to not P and not Q. Remember, these are called De Morgan's laws. And they're crucially important in mathematics. We use them all the time, even if we don't explicitly state them here. So this is our primary vehicle for negating any statements that have an and or an or. Let's go ahead and take a look at an example. So here's a statement. You can solve the equation x squared plus 4x plus 4 equals 0 by factoring or with the quadratic formula. So this is our statement right here. This is the statement. And let's suppose that we want to negate this statement. So our goal for this example is to find the negation or not this statement. So first of all, let's express this in terms of our logical symbols here. So let's suppose that P is the statement you can solve, and I'm going to save time. I'm going to label this as equation 1 right here. So I'm going to put 1 in parentheses. And as you read a lot of mathematical textbooks, this is a very common way of abbreviating equations or long statements. You don't have to keep writing them over. So I'm going to say that P is the statement you can solve equation 1 by factoring. And then Q will be the statement you can solve equation 1 by the quadratic formula. And then our original statement is going to be, of course, P or Q. You could do it this way, or you could do it this way. So this is the original statement, but now we want to find the negation of this. When we want to negate this, we invoke De Morgan's laws up here, and our negation will be not P and not Q. All right, so now we know what our negation is in symbols. So let's go ahead and write out the negation in English here. So here's the negation as an English sentence. So now we're going to say you cannot solve 1 by factoring. And instead of the or that we have back here, we're going to use an and instead. You cannot solve 1 by factoring, and you cannot solve 1 by the quadratic formula. All right, so there we go. So there is negating a statement. Oh, by the way, which one of these is true? Is this the original statement true, or is the negation the true one? The original, that's right. So the original one was true, so necessarily the negation of this will end up being false. All right, so there's our first example with negating and or. Let's take a look at another example here. Here's a statement, rather an open sentence, I suppose. The numbers x and y are even. So the truth or falsehood of this sentence right here depends on what x and y are. We could still find a negation of it. So in this case, rather than using or, we're instead using and right here. So if we wanted to negate this right here, we would say that either x is not even or y is not even. So remember, the way we negate and or is we change the and to an or vice versa, and then we negate each of the individual statements. So the individual statements being combined here were the number x is even and the number y is even, so we negate each of those individually. So we have either x is not even or y is not even. So at least one of the two here is even, if possibly both. All right, any questions on negating and or? They essentially boil down to just De Morgan's law. All right, so now let's go into something that's a bit more difficult to negate. Let's say we wanted to negate, that's not how you spell negate, there we go. We want to negate there exist or for all statements, or these quantifiers that we learned about last class. Let's suppose we want to negate a statement with those. Well, in these cases, remember that the for all quantifier is kind of like an infinite string of ands, and the exists quantifier is like an infinite string of ors. So kind of like how or flip to and vice versa here, when we negate their existence for all, we're going to replace one with the other. So that's how we negate these statements here. So here's the general rule. So let's suppose we wanted to negate the statement, there exists an x contained in some set x such that p of x is true. So this is some statement, and this is saying there is an x in this big set that makes the statement. Let's suppose we wanted to find a negation of this. Then what we would say here is we would change the there exists to a for all, so the upside down a. So for all x in this set, we say that the statement is not true. So kind of like how we did back here with De Morgan's laws, where we flipped the and or, and then we negated the statement as well, we're doing the same thing here. We're flipping that there exists to be a for all, and then have the not be an x. Why not use a comma here? Well, you can use a comma here. Remember, the comma and the colon are somewhat interchangeable here. You can use either one. I kind of agree with you, actually. I think the comma would make a little more sense if you were translating directly to words. But yeah, we can remember, we could use either one. This is saying that the negation of this is for every x in the set x, it's not true that p, which is the opposite of saying there is an x that makes p true. And of course, on the other end of things, we can negate a universally quantified statement, remember with the for all. So if we want to negate the statement for all x, this property, I'll use a comma here, this property is true, then we would say that there is an x out there such that the statement is false, like that. All right, so this is how we negate there exists and for all. We flip which one we're using here, and then we negate the statement. And that's going to be true anytime we negate the statement. All right, let's go ahead and look at some examples of this right here. So here's our first example. So for all x in the interval 0 to 3, we have that x squared is less than or equal to 9, like that. All right, so this is our statement here. And our goal for this problem is to find a negation of this statement. There's our example. Let's think about what the negation is. All right, so following this paradigm back here, we switch the for all to be a there exists. So what we're saying is there is an x, and we don't change what the set is. So this set wouldn't become the opposite or the complement of this set. It wouldn't go from -infinity to 0 and then 3 to infinity. This set stays exactly the same. And that happened up here as well. But what we will change is we will negate the statement x squared is less than or equal to 9. So the negation of that statement, well, if you're not less than or equal to something, that means you must be greater than that number. So there exists an x in this interval such that x squared is greater than not. So that is the negation of the statement. And besides procedurally following along with this, let's make sure that we understand intuitively why this is happening. Let's think about what the first statement is saying. This is saying that no matter what x we pick in this interval, if we square it, it'll be less than or equal to 9. By the way, is this a true statement or a false statement? Is this true or false? Right, this is true. If you take any number from 0 to 3 inclusive and you square it, it will certainly be less than or equal to 9. All right, so we're saying that all of the numbers, no matter which one we take from 0 to 3, all of them will satisfy that property. Any number we pick in here will make this work. Okay, now what is negating this statement? Well, if we want all of them to work, we can mess that up by finding one that doesn't work. And that's what the negation is saying here. So the negation is saying there exists an x in this interval. So what this is saying is somewhere in this interval, we can find an x that does not follow this rule. So we can find an x in here that is not less than or equal to 9, and that's the same thing as being greater than 9. And of course, since this statement was true, its negation must be false. No matter how hard we look in this interval, we can't find an x that will break this rule right here. So this is going to be false. But make sure you understand why the negation of a for all is there exists. It's because you're trying to find effectively a counterexample to this statement right here. All right, does anyone have any questions on this example right here? All right. Let's move on to another one. We're going to practice with a few of these here. Let's take a look at another statement. All right, so our example here is there is an even integer. So here is our statement. Now, this time our statement, if we were to write it out in symbols, actually uses a there exists. So if we were to write this out in symbols, what we would say is there exists an n in z such that there exists an m in z where n is equal to 2 times m. Like that. That's what saying there is an even integer turns into symbolically. So there is an n in the integers, and there's also an m such that n will be 2 times that n. All right, so let's go ahead and negate this statement. So the negation of this statement is pretty clearly there is not an even integer. I think it's pretty clear which one of these is going to be true. There is not an even integer. So let's go ahead and see what that would be in terms of symbols. What we're saying is that if we look through all of the integers and we pair it with any other integer, and by the way, we could shorten this by doing n comma m in z as well. In fact, I'm going to do that. For all n and m contained in z, what's going to happen is n will not equal 2 times m. So no matter how many different combinations of integers we look through in the whole set of them, there's no way that we can write one integer as 2 times another. So that's what this statement is saying here. So remember, once again, we change the there exists to a for all, and then we negate the statement itself. All right, so there we go. So that's going the other way. That's turning a there exists into a for all through negation. Now, as we saw last time, things can get a little bit complicated when we have both a there exists and a for all mixed into our statement together. But this rule will still apply. What we're going to do is we're going to flip any there exists to be a for all. We're going to change any for alls to be a there exists, and we're going to negate the statement. So it doesn't matter how many of these appear or in what order they appear. We keep the order the same, we just flip all of these symbols and then we negate the statement. So let's go ahead and look at another example. This one will be a little bit more complicated than the ones we've seen so far. So the next statement is, there exists a function f in this set right here. C, and then we have a parentheses and then an R here, and I'll explain what that means in a second. There exists an f in this set such that for any x that is a real number, we have that the absolute value of f of x is less than or equal to 1. All right, so if I'm being clear here and I'm doing my job as a mathematician, I should clearly explain what everything in this statement means. And I think we already established what R is, and we know what this is back from algebra, but we should establish what this is. So CR is the set of all functions from R to R. So this is the set of all real valued functions that take a real number and give you another real. So this is the set of all functions from R to R, or functions f, I should say. Functions f from R to R such that f is continuous. So this is the set of all continuous real valued functions. And what this statement is saying, so let's dissect what this actually means. This statement, actually, let me ask you all. Does anyone care to explain either in the chat or verbally what this is saying? What is this statement telling us? And is it true or not? Is this a conventional set, or did I define that? This is the conventional notation for this set. Usually when you see C and then you have parentheses right here and then some other subset of the real line, that's continuous functions with this as a domain. So that is common notation. Some people also may put it as C0. That also you will see. Oh yeah, anyways, what is this statement saying? The range of functions are in the range. Well, it's not really saying that about all of the functions. Let's see, Harrison, there's a function where every value is between -1 to 1. That's right, yeah, but it would be including those, but yes, they don't have the equal to symbols on them. That's right, Harrison has the right idea. What this is saying is that there is a continuous function out there such that for any real number, the absolute value of that function will be less than or equal to 1. Yeah, hard to type on the phone, yeah. And can anyone come up with first of all, is this true? Is there a function like that? Is there a continuous function that satisfies that? We do that? Yeah, all right, yeah, people are giving some examples already. Yeah, so some very common functions have that property. So for example, sine of x has that property. So the absolute value of sine of x, as we know from trigonometry, always has an absolute value less than or equal to 1. And it's continuous, and it's defined on the real numbers. So sine of x would be an example of this, as well as cosine. The constant function 0 does this, as well as any constant function that's equal to something with absolute value less than 1, like 1/2. So it turns out that there are a lot of examples, but all we really needed was one. We just wanted one to exist. And since at least one exists, this is going to be a true statement. Okay. So now that we know what this statement is talking about and saying, let's think about what the negation of this statement is saying. Let's do the negation here. So first of all, let's mechanically go through and apply what we learned. So remember, we flip any there exists to be a for all. We flip any for alls to be there exists, and we negate the actual content of the statement itself. So when we do that here, we have that for every continuous function defined on the real numbers, there exists a real number such that the absolute value of our function is greater than 1. Okay, so now since we established that this is true, we immediately know that this one's going to be false here. So we kind of just know that logically speaking, since the negation of a true statement is false. But let's think about mathematically why this is going to be false as well. Let's dissect what this is saying here. So what this is saying is that for every continuous real valued function, so no matter what we're looking at here, no matter what continuous function we pick, you can always find a number where the absolute value of the function, when we plug in that particular number, is bigger than 1. And we already know that this is going to be false. And let's think of some examples. In fact, the examples that will make this be false are precisely the same examples that worked over here. So this is saying that no matter what continuous function we pick, we should be able to find a number that makes the function be bigger than 1. Well, can we do that with sine of x? Can we find an x that makes the absolute value of sine bigger than 1? And the answer is no, we can't do that. No matter what real value we plug into sine, which is a continuous function, it's in this set, then we're not going to be able to find an x value that makes this be bigger than 1. So we can see, even if we didn't know this previous statement was true, we could definitely see that this statement is false, because we were able to find one that this would not work. All right, but once again, the moral of the story here is that, at least mechanically, we can flip any exists to be a for all, any for all to be there exists, and then we negate the statement itself. Malek, you said is not continuous. Wait, what were you? Okay, all right. Yeah, remember, so I don't know if this is what you're talking about, but remember, the set itself stays the same. So we don't start looking at the set of non-continuous functions. The set that you're looking at remains exactly the same. That's one of the things that doesn't change in these negations. All right, so there we go. So there's some examples of that. And one final thing we can do here is, or one thing I want to go over, is I want to talk about the negation or negate and implication. So for example, let's say I want to find the negation of P implies Q. So as we're going to find out in chapter 4, many of the most common mathematical statements we can make are in the form of implication, where we say, oh, if we have this hypothesis, then we have this conclusion being true. That's probably the most common form of a mathematical statement. So let's suppose that we wanted to negate this and see what its logical opposite is. Well, let's go ahead and do some arithmetic or algebra with the logic here, using logical equivalence. Let's say we start with not P implies Q. So I hope the substitute talked about this on one of the days I was gone. So there's actually a way to write implication in terms of the or operator on statements. So does anyone remember what the implication is equivalent to in terms of or? That's right. Yeah, so it's not P or Q. So what we could do is we could replace the implication inside this parenthesis with not P or Q. Remember, that's exactly the same thing as the implication right here. Because with implications, when your P is true, we want Q to be true. So that's this part right here. Or we just have P being false and we don't even question the implication. So that's this. That's why these are the same. And also on a more fundamental level, they have the same truth. Okay, but the thing now that we're doing is we're negating an or statement, right? So we literally talked earlier today about how to negate an or statement. What we do is we flip the or to be an and then we negate each of the statements here individually. So we have not P, and then we have not Q. So we have that with De Morgan's laws here. And then finally, there's one way we can simplify this further. What might be a nicer way of writing this right here? One more fact we can use. Right, yeah, so we have a double negative here. So we have not P, which just means P. So if you do negation twice, it more or less cancels out with itself. So we have P and not Q. So this is going to be our most common form of our negation of P implies Q. And on a certain level, this makes sense, because if you remember the truth table for P implies Q, there was only one section of that truth table that was false. It was when P was true and Q was false. That was the only time that this implication didn't work. So it makes sense that the negation of this will be when we have P being true and then not Q. This is going to be our negation of our implication. All right. And this one's a little bit weird because for all of the other negations, we kind of had a pair of things that we flipped between. But here we have an implication, and we don't really get another implication out of that. We actually just get an and statement. So this has a little bit of a different feel than the others. I'm going to give one example of this, and this will also have us continue practicing our skills with the quantifiers. So let's take a look at an example of this statement. We have the limit as x goes to a of f of x equaling some value L. So in terms of calculus, this is saying that the limit as x approaches a of our function is equal to a particular limit value, which is L, some real number. All right. Now, yesterday, I gave us a way of expressing this in terms of our quantifiers. And this is something you're going to do all of the time if you take advanced calculus. You're going to use this particular thing I'm going to write here. So the statement of this in terms of universal and existential quantifiers is for every epsilon greater than 0, there exists a delta greater than 0 such that if x minus a in absolute values is less than delta, then f of x minus L is less than epsilon. All right, so there's our statement in terms of our quantifiers. And remember what this is saying. This is saying that if we want to get really close to the value L, so this epsilon is tiny right here, then what we could do is we could find another tiny distance, delta, such that if our input is close enough to A, then our output will be close to L. That's what the limit is saying, and that matches up with our intuition. As our input gets really close to A, our output will get really close to L. Okay, so there's the original statement right there. Does anyone have any questions about this delta epsilon definition here before we go to the negation of it? Okay, now notice that the delta epsilon definition here, this has as part of its statement, as the kind of meat of its statement, an implication. So we're going to be negating that, meaning that we're going to use this right here. So P and not Q. All right, so let's write out in symbols what the negation of this would be. So the negation of a statement, well, we have an equality here. So if we're going to negate an equality, it's just going to be an inequality. So we have the limit as x approaching a of f of x is not equal to L. Perhaps it's equal to some different number. Perhaps it doesn't exist at all, whatever. There's just this negation of this statement is saying that it's not going to be L. That's much as true. All right, so let's mechanically carry out the negation of this statement. And then let's think about what it actually means mathematically, rather than just grinding through the formula. Okay, so first off, we have a for all epsilon greater than 0. So that means that this is going to transform into there exists an epsilon greater than 0. And this there exists a delta greater than 0 means that we're going to have for all delta greater than 0. All right, and then afterwards, we have the statement itself. But remember, we're not just going to flip the order of the implication. That's a common misconception. That's not just going to be the negation of our implication here. The negation is going to be this hypothesis, P, and not the conclusion. So the negation of this is where we have this being true, but then this not happening regardless. So This will be our statement P. So we're going to have x minus a is less than delta, and we're going to have absolute value of f of x minus L being greater than or equal to epsilon. Okay, there we go. And in this situation right here, it may actually be more stylistically correct to use the word but. And remember, but means the same thing as and, although it shows up often with a negative connotation or in negation. All right, but this still means the same thing as and right here. You could use and it'd be 100% correct. All right, so let's go ahead and dissect what this actually means. Actually, I want to give this to you and see if someone can come up with an explanation of what this negation is saying. So remember, the original limit means that as our input gets really close to A, our output gets really close to L. So then what would this limit not being equal to L say? How would you explain how this means this limit is not? Asymptotes? As our input gets closer to A, the function gets further from L. Both of those ideas are somewhat correct. You're thinking along the right lines here, but then neither of those are exactly right. Anyone got any other ideas? Remember, try to read through this. There exists an epsilon greater than 0 such that no matter what our delta is, this is true, but that's true. It diverges. Well, it's certainly, we don't know that this limit does not exist, for example. We just know it's not going to be L. It could be some different one. All right, let me explain how this is going to work here. So the original statement says that no matter what tiny distance we want, meaning no matter how close we want to get to L, there's always another tiny distance delta, such that if our input is that close to A, then our output will be this close to L. Now, let's see, there's a value that is always less than the difference of X and A, no matter how close they are. Yes, that is, yep, that's exactly what it is. Yeah, good job, Henry. That's right. So that's exactly what's going on here. So what this is saying now in the negation is saying there is a tiny little distance such that no matter how close you get, so we use any distance between the inputs, we can get that close to A, but we can't get any closer than epsilon to L. So no, even if we go to A itself, we're still not going to make our f of x get really close to epsilon. There's a limit to how close it can get. And that limit to how close it can get is epsilon. Maybe, for example, epsilon is like 1/2. Then what this would be saying is that no matter how close we got to A, our function could not get within 1/2 of the L. And if we draw a picture, this will become a bit more clear. So let me get a paper, draw the picture. So let's suppose that we have maybe this. Here's our A. Here's A minus delta, A plus delta. And then let's say our limit is not where we would expect it to be, like right here. Let's say our limit is right here. So what we're saying here in this statement is that no matter how close we get to our A, so no matter how much we come in on either side right here, then we're not going to make our function get any closer to this L down here. So that's why this would not be the limit of our function here. And our epsilon, for example, that would work, an epsilon that would work for this might be this right here. No matter how close we make our input to A, we're not going to be within this distance of L. Well, why would the limit be so far from the actual value? Well, that's just, this is a negation. So this is saying that this is not the limit. So this is what not being the limit means. So for example, let's use a concrete example. Let's say that the limit as x approaches 1 of x squared plus 1 is not equal to 0. So here's an example of this. So what would we say here? What would the statement in terms of these be? It's saying that there exists an epsilon greater than 0 such that for any delta greater than 0, we have the absolute value of x minus 1 less than delta is true, but we have that x squared plus 1 minus 0 is greater than or equal to our epsilon. And our epsilon in this case, we could pick epsilon equals 1/2. So for this, here's x squared plus 1. It's a parabola and it's shifted up by 1. Here's our function. Then here's our limit L equals 0 down there. We're saying that this is not the limit as we approach 0. So here's our A value, which is 0. And no matter how far we go, either to the left or to the right of this, we're not going to be able to get within 1/2 of 0. So no matter how far we go this way, or how close we get to the middle here, we're not going to be able to get within 1/2 of 0 here. That would be what this statement means right here. And in practice, Rowan, no, you wouldn't, usually don't care what the limit isn't, you care about what the limit is. So this negation is probably a less useful statement than this one is right here in general, but this would be what it actually means if we were interested. All right. But the moral of the story here is that the negation of quantifiers will just be the other quantifier, and then the negation of implications will be this and statement right here, which you can often use the word but. All right, does anyone have any questions on this example right here? All right, and I just want to offer the disclaimer. This is just an example of me illustrating this concept in an actual mathematical topic. I'm not going to put delta epsilon stuff on the exam. I'll save that for when you get to advanced calculus. Then they'll put that on the exam or whatever you have to do there. So I'm not requiring you to know that the limit definition or the delta epsilon definition of the limit in calculus is this right here. So you don't need to have that memorized or anything or need to know that. So don't worry about that. That's just, I'm just using it as an example of where we would use all. All right. So there we go. That's section 2.10. All right. So there's 2 more sections in this chapter here. So 2.11 is going to be talking about logical inference. All right. So 2.11 is one of those sections where this stuff is so obvious, you're like, why are they even bothering to explain this? But that actually is one source of difficulty in mathematics. Sometimes a truth is so obvious that you don't even notice it or you don't even consider it. And sometimes the truth is just sitting right there in front of your face and it's so obvious that you wouldn't consider using that in a proof of something. So that's one thing to be aware of, is that sometimes the answer could be so simple it's sitting right in front of you. And that's essentially what this section is doing. It's giving you a few logical inferences that are pretty obvious, like you definitely know all of these are true already, but they're that kind of things to keep in the back of your mind if you get stuck on a problem. So the first one is that let's suppose that we have the statement P implies Q, and this statement is going to be true. So this is going to be true. And then let's suppose also that the statement P itself is true. So if we know that both P is true and P implies Q is true, what can we conclude from both of these statements being true? What also will have to be true? That's right. Yeah. So Q will also have to be true. So with P implies Q and P, we could also get Q. So this is one logical inference where we can put 2 statements together and then find the truth or falsehood of a new statement. And this particular inference has a particular name. It's called modus ponens. But honestly, you don't really need to know the name of that. You'll never, rarely, I guess, open up a mathematical proof, be like, we're using modus ponens in this proof. So it's just kind of the formal name for it, but you don't, it just is there. There's also another one with a bizarre name, modus tollens. So this one also has to do with P implies Q, but this time the other true statement that we have is not Q. All right, so let's think here. If we know that P implies Q, and we also know that Q is not true, then what can we say about P? What can we conclude here? Yeah, P, yeah, so we're gonna have not P in this case. We have P implies Q and we have not Q, then that means that P wasn't there. Because if P was there, then we would have gotten Q, but we know we don't have it. So this is another one. I guess this one's a little bit less obvious than this one is over here. And finally, there's one that has in a name that's actually not very fancy sounding called elimination. So this time, we're given that P or Q is true. And we also know that not P. So we have not P here. Well, if we have P or Q and it's not P, well then what does it got to be? Q. That's right. This one's especially one of those ones like, okay, that's so stupid. Like even like a baby knows this one pretty much. But oftentimes in mathematical proofs, they may give you this information right here, P or Q, and you can later conclude that P is not going to be the case. So in that situation, then you know that Q is going to be true. And it may seem obvious here when it's written out explicitly on paper, but it's honestly a pretty useful technique. Here are a few other ones that are even more boneheaded, but again, even though these are obvious, there are things that you want to be explicitly aware of in some instances. So let's suppose we have P being true and Q being true, then what else has to be true if both P and Q are true? Yep, I literally said the answer. Yeah, so it's going to be P and Q right here. All right, here's one that is actually a bit subtle, and this one's helped me a fair bit on some of the proofs that I've done before. So let's suppose that the only statement they give us this time, so this time we're not going to give two hypotheses, this time we're going to have one. So this time we're going to suppose that P and Q is true. What else do we know is true simply based on this right here? That's right. Yeah, exactly. Yeah, it's so obvious you think like, oh, that can't be the answer, right? But yeah, no, we know that P is true, and we know that Q is true if their and statement is true as well. And this one in particular, it's kind of hard to spot in the moment. So you have both P and Q being true, so you feel like you need to use both of this pieces of information, but sometimes you really only need one of these. So you may have P and Q being true, but all you really want is just P. You get that automatically. And then we have something going the other way. So suppose the statement P is true, then we automatically get for free that P or Q is going to be true, no matter what the other statement is. It can be something insane here, but as long as we know that P is true, then we know that P or Q is automatically true because P is picking up this. All right, so that's essentially what this section is reminding you of, these kind of ways to combine two logical statements or maybe one logical statement together to get new information. And that's effectively the business of mathematics, is taking known statements and properties and producing new ones from them. And these are some of the primary vehicles with which we do that, even if it's behind the scenes and even if we don't directly call it modus ponens and modus. All right, that's 2.11. And then 2.12 is an even smaller section, effectively talking about why we even bother having this chapter at all. Because a lot of these things, especially in this previous section, are obviously true, and you knew them, and people who would never take this class would also know that these things are true, even if they didn't know the symbolic way of writing math. So why are we even messing around with this to begin with? I mean, this is so kind of boneheadedly obvious. Well, effectively what the author is saying here is that logic is the glue that holds mathematics together. And I think everyone kind of knew that already, but because it's so crucially important, we want to kind of get some practice and exercise with using just basic logic here. We want to get practice with that because essentially that's the core of what holds all of mathematics together. We're going to kind of stretch our legs a little bit by doing this, but then when we move on to the future, i.e. the next chapter here, we're not really going to write a lot of these symbols, at least not as often. We're not going to directly use a lot of pure logic, but it is good to kind of have these floating around, especially things like this, in the back of our mind when we do mathematics in the future more generally. So that's effectively what they're saying here. One thing I want to add, though, is that logic can be studied in its own right. So despite being such a foundational subject that's relevant to humanity, I mean, we're logical beings, we live in a logical world, there are still new things being researched and discovered in logic, and in particular in the logic that has to do with mathematics. Actually, here at the University of Florida, that's actually one of the research specialties of the school, is mathematical logic. There are a few famous logicians here. So if you are interested in kind of going deeper into just logic itself, which is an interesting field, let me know and I can direct you to one of them. I'm not one of those people. I'm not a logician or someone who researches mathematical logic. I can definitely point you to a lot of people that would definitely be more than happy to talk to you about all this. All right, anyway, so that's it for chapter 2. Anyone have any questions about anything logical that we did in chapter 2 here? All right. So what we're going to do now is we're going to actually skip chapter 3. So chapter 3 has to do with the subject of counting. And you might think, oh, great. Okay, here's another thing that I've been doing since I was a baby that we're going to talk about in the college level class. Like, why are you wasting my time here? And it turns out that counting is another detailed subject in mathematics that you wouldn't expect there to be research in. The formal name for it in mathematics is called combinatorics, so you have combinations or counting. And usually problems in that field of study are like, if you have 10 shares and you have 8 students, how many different ways can you arrange the students in those chairs? That's an example of a combinatorics question. And it's often a nice entry point for thinking logically and carefully about mathematics. So that's what chapter 3 is about. And if you are interested in that, I encourage you to read it on your own. You can ask questions about that to me in office hours. We're going to skip that for now. And there are classes at UF that do that specifically. So if you are interested in that, there are classes that are focused specifically on counting, as silly as that seems. We're going to skip that, and we're going to move to the meat of the course, effectively the main goal of our course, which is learning how to write mathematical proofs. And that's going to be what we begin talking about in chapter 4, and that's going to be the subject of everything else that we're going to do in this class. Effectively, the sets and logic part, chapters 1 and 2, that's sort of like a prerequisite for going into proofs. Now we've established all of the notation and the subjects we're going to be looking at. All right, so let's go ahead and move on to chapter 4 then. Over here. All right, so chapter 4 has to do with what is called direct proof. Before we talk about that, I kind of want to talk about proofs in general. So let's zoom out really big for a moment here. So one could argue that the primary goal of mathematics, and by extension, a mathematician, a practitioner of mathematics, is to prove theorems. So for pretty much every mathematician working in Little Hall or any other university or doing anything, if you're doing mathematical work, you're primarily concerned with proving theorems. Now, this isn't the only consideration of mathematicians. Like there are many computational mathematicians that carry out numerical experiments. There are also mathematicians that focus more on building a theory or a collection of theorems. But by and large, the bread and butter of mathematical work is proving theorems, and you prove theorems in those other activities as well. So this is the primary goal of mathematics, and whenever you're doing math, there's likely going to be theorems behind what you're doing, and so proving them and establishing the validity is of utmost concern. Let's go ahead and establish some terminology here, and likely, again, these are the things that you've heard of, but I just want to lay them out explicitly. So we want to prove theorems. All right, so what is a theorem? So a theorem is a mathematical statement. So it has a logical truth value that is true. You don't want false theorems, and can be shown to be true. So not only is it true, maybe in like a self-evident kind of way, but there's a way that we can show or prove its validity. So these are the two requirements. It's true, and it can be shown to be true. There are certain things that we accept as true without proof. Those are considered axioms. Those are things that are so obvious and self-evident that we just accept those are true without proof. And often in mathematics, we want to minimize the number of axioms, and we want to show where mathematical statements come from. So ideally, we want to have as few of those as possible. We want to try to show proof for as much as possible. All right, so let's go ahead and define what a proof is then. So a proof is a written, although this is now contentious nowadays, a written verification that a theorem is true. So when we write out a mathematical proof, we need to make sure that it's 100% clear to whoever we're communicating with what our assumptions are, what logic we use, and why the theorem is going to be true. So we have a question from Merlin: do axioms ever become theorems or vice versa? And the answer is, it really depends. So one thing I want to talk about next, and this actually has to do with your question, are definitions. And I'm going to give a definition for a definition here, and then I'll answer your question. So a definition is a clear and unambiguous explanation of the meaning of a word or phrase. Now, oftentimes our definitions are very similar to our axioms. We're saying what something is precisely and in a clear way. However, in mathematics, there are times where we can define thing A and then show it's the same as thing B, or we could take as a definition B and then show that's the same thing as A. So it kind of depends on your perspective. And an example of that is the number E. So everyone's familiar with the number E, right? 2.71, A2A, like that. So here's one definition of the number E. So E is defined as the limit as n goes to infinity of 1 plus 1 over n to the n. Like that. Hopefully you've seen this in calculus at some point. This is a very common definition of the number E. However, this is not the only definition of the number. You could actually get E elsewhere. So another definition would be E is the real number greater than 1 such that the derivative is the real number, I guess I'll call it A greater than 1, such that the derivative of A to the x is equal to A to the x. You can make a legitimate definition of E by having it be the unique real number that when we differentiate it to the x power, it remains as the same function. You could define E in that way. And depending on which one of these perspectives you come from, and there are actually others as well, there are other ways of defining E, you could either start from here, start from this being the definition of E, you take this almost as like your axiom, and then you prove that this is true. Alternatively, what you could do is you could start here with this definition of E, and then prove that that is true. So to answer your question, the answer is yes. So sometimes we choose what we want as an axiom based on convenience, and then we get to something else that's a theorem, but in another perspective, we could totally flip those around. And for a historical instance of that, you know, there's like Euclid and his geometry and the 5 axioms. There's the axiom called there's the axiom called the parallel postulate, which was assumed to possibly be a theorem that you could prove based on the other axioms, but it was later shown to be that no, you need to have this as an axiom. So yeah, so there's a whole rich world to all of this, is what I'm trying to say. And it can be different depending on your perspective. All right, so now that I've elucidated what all of these words mean, we're going to try to familiarize ourselves with the primary goal of mathematics. We're going to get more acquainted with proving theorems. And as I said on the first day of class, unfortunately, there's not just like a cut and dry formula for proving any generic theorem. That would make it so really anyone could do mathematics. Well, let me rephrase that. Anyone can really do mathematics, but the way you prove theorems is going to be different in many different instances. So it's not something you can make an algorithm to do. You can't just have a computer like plug in the proving algorithm and then have the computer do all of the work for you. Although nowadays, though, there is actually research into computer programs that can prove theorems. That's actually a point of controversy and contention in mathematics is a proof that is done by a computer considered legitimate? Is that something you can actually do? And most mathematicians say yes, but there are a lot of arguments about that. But anyways, back to our goal here. We're really trying to just get acquainted with proving theorems and how that works and how that is often done, even if there isn't a set procedure for that. So what we're going to do for the rest of the class today is I want to kind of illustrate some pitfalls or more some things that we do not want to do when we're proving theorems. So what I'm going to do here for a second is I'm going to stop sharing this, and I'm going to go ahead and share my internet here. We're going to watch a quick little video about proofs. And some of you may have seen this before. Can everyone see YouTube here? Everyone see that? Okay. So what we're going to do is we're going to watch a proof to see that we're going to watch a little bit of a proof about a division concept. And this is given by Lou Costello, who is a comedian in the early 20th century. Everyone hear that? Everyone hear the sound? Oh no, you can't hear the sound. Wait, hold on. I didn't hear the sound. Oh, how do I share with audio? And sharing options. Little checkbox at the bottom. Let me try it again. Oh, share sound. There we go. Okay. Thank you. Thank you.
18 weeks at 7. Mr. Landlord.
Yeah?
All right, can people hear it now?
Smoking an army blanket?
Never mind about that. You owe me room rent.
All right, here's $28.
All right,
$28, fine.
let's watch a little movie.
Just a minute. You owe me 13 weeks at $7 a week, and that happens to be a lot more than $28.
Well, that comes to $28.
Did you go to school?
Yes, sir.
Do you mean to say that you can prove that 7 times 13 is 28?
Well, it's got to be. Certainly it is, because Mr. Rabbit and I, that's $28. That's what you get.
If you can prove it, I'll tell you what I'll do. I will give you the room rent for nothing.
You will?
But if you don't prove it, you owe me double the back rent. Is it a deal?
That's a deal.
Okay.
You happen to have any Crayola on there?
Crayola?
Never mind. I got it.
Oh, you have?
I got the Crayola. The 7 into 28 is going to come out 13.
That's your way.
That's my way. And it's got to come out right. Now, first,
I also love how they just start
right?
writing
Now,
on the wall.
I'm going to divide the 7 into 28.
Yep.
I put a 28 there.
Okay.
Isn't that cute? Now, here we go. 7 into 2. 7 will not go into 2.
It will not.
That's a very big 7 to push into that little bit of 2.
As you say it is.
We ain't going to hurt that little 2, are we?
Of course you won't.
So we take the 2. Open your hand.
Yes.
And I put that 2 right there for safekeeping. But don't drop it and don't lose it. Now, 7 into 8.
Once.
Once. I put the 1 over here, 1 over there. Now, we're going to carry the 7 because it's very big and it's getting heavy on my shoulders, and I'm going to drop the 7 under there. Now, 7 from 8
Is 1.
is 1. I put the 1 down there.
Mm-hmm.
Now it comes. Would you mind opening up your palm of your hand, please? Or would you like to use that 2? Open it up. Give me that 2. You've had it long enough. I'm going to put that 2 right there. Now, 7 into 21.
3 times.
That's right. 7 into 28. 13. Good enough?
Wait a minute. You have to prove this even better than that. You can prove it very easily by multiplication.
You mean you want me to emulsify it?
No, not multiply, multiply.
Emulsify.
Multiply.
All right. All right. Multiply it.
7 times 13
It's
prove
28.
it. Go ahead.
Now, first, we got to put down a 13, right?
Right.
There's a 13.
Times 7.
Times 7.
Right.
7 weeks times 13, right? 7 times 3.
21.
21. 7 times 1.
7.
7. 7 and 1.
8.
And 2 to carry. 28. Wait this out.
Now, wait a minute. I'm still not convinced. There's one sure way of proving this. One sure way, and that's by addition.
You want me to addition it up?
I want you to put 13 7 times on that wall and then draw a line and add them up.
You want me to put down 13 7 times?
That's right.
That's got to come out right. There's 1,
1,
2,
2,
3,
3,
4,
4,
5,
5,
6,
6,
7.
Wait a minute. What's the idea of spreading them out like that?
Well, it looks like a flock of seagulls going to hit the electric poles. Now we're going to add them up, right?
All right, go ahead.
Here we go. 3, 6,
Wait a
9.
minute. Let me do the adding this time.
Good. Come out right.
Well,
A 3, a 6, a 9.
Just a minute. I will do the adding. Then there'll be no mistake.
Yeah?
All right? $28 here. All right?
Sure.
Now.
Go ahead. You had it up. Go ahead.
3, 6, 9, 12, 15, 18, 21.
22, 23, 24, 25, 26, 27, 28.
All right, there we go. There's our little proof of the day here. So clearly I know that, I know, of course, you know that, 7 times 13 is not going to be 28. I'm not really questioning your arithmetic here. But what I wanted to illustrate with this little video is that when you're doing some kind of mathematical proof, when you're explaining things to someone else who's reading your work, clarity is of utmost importance. When Lou Costello was, doing his magic on the board there, he was kind of just putting numbers in random places and doing things without explaining why he was doing them at all. And of course, it's a joke, but that's essentially why that's not a valid proof that 7 times 13 is 28. Yeah, I can't believe my elementary school teachers never told me that. Yeah, yeah, exactly. It's a new fact. So what we want to do, yeah, $7. Yeah, I know. Even if it were $91, like I would still take that. $91 for 7 weeks. Yeah, exactly. So, but anyways, with that video, I wanted to explain that when we're writing up proofs, we want to be extremely careful and very thoughtful about how we present our information and our reasoning. So effectively what Lou Costello did was a sort of mathematical trick. So he effectively just did a magic trick. And when you do a magic trick, the whole point of a magic trick is to start at point A and then go to point B and have the audience be surprised when you get to point B and have no idea how you got there whatsoever. And, you know, magician never reveals the secrets at all. Effectively, what I want to establish here is that a mathematical proof is almost the opposite of a magic trick. What you want to do is you want to start at point A and get to point B, but you want to reveal all of your secrets along the way. So you want to show the reader or whoever your audience is exactly what you're doing and exactly how you're doing it every step of the way. And then it's no surprise at all. In fact, it's really obvious once you do get to B. So that's what we're trying to do when we do a mathematical proof. We're trying to get from A to B, and we're trying to make it as clear as possible why we're writing things the way we are, why we're doing things the way we're doing them. The better, the more we elucidate that, the better when we're doing a mathematical proof. One other thing I really want to illustrate, and another common pitfall that happens when we first start considering proofs. Let me go back to the paper here. This is probably the biggest pitfall that people first starting out proving things in math go through. So here's the warning for this. Specific examples don't prove the rule. So it may be tempting when you're trying to discover new mathematical facts to try a bunch of different examples and see what happens. And I'm not shaming that, or I'm not saying that you shouldn't do that. Oftentimes that could be a good way of building up intuition. However, writing down a bunch of examples where something is true does not verify that it's going to be true in general. So what I want to do is I want to kind of give a cautionary tale of this. So what we're going to do is in this example, we're going to start with the prime numbers. So the prime numbers are 2, 3, 5, 7, 11, 13, etc., like that. And what we're going to do is we're going to divide by 4 and then see what the remainder is. So when you divide by 4, there are 4 possible remainders, 0, 1, 2, 3. And what we're going to do in this little exercise is we're going to see what the most common remainder is when we divide prime numbers by 4. So let's break it into categories. We have remainder 0, remainder 1, remainder 2, and remainder 3. You can't have remainder 4 because then you could fit another 4. Okay. How many prime numbers do we expect to have in this column? Then we divide them by 4 and have no remainder. How many do we expect to see in here? Is 0. Yeah, why is that? Why do we automatically know there's not going to be any in this column? Yeah, it wouldn't be prime. That's right, because then they would be evenly divisible by 4, and that means you're not a prime number. So we immediately know that 0 is going to lose here. We're not going to see anything in there. Now 2, we will see one number in here. 2 divided by 4 has a remainder of 2. But will we see any other numbers in this list right here after 2? Yeah, so if we start going here and we divide a number by 4, yeah, Ronan has the right idea here. Because if you divide a number by 4 and it has a remainder of 2, that means it's an even number. The only even prime number is 2. So that means 2 is probably going to get eliminated here. So we're really just looking to see which one of these 2 is going to be the biggest list. We're trying to find out whether prime numbers have more remainders of 1 when divided by 4 or more remainders of 3. Let's start going through the list. So we divide 3 by 4, and we get a remainder of 3. We divide 5 by 4, and we get a remainder of 1. Okay, well, so far it's neck and neck. We divide 7 by 4 and have a remainder of 3. And then we divide 11 by 4, and we also get a remainder of 3 for that as well. All right, so it seems like the 3s are taking the lead here. Next, we go to 13. 13 divided by 4 will have a remainder of 1. The next prime number will be 17. Oh, it looks like it caught up again. But then 19 will be over here. followed by 23, and then 29 will be here, and then 31 will be here, and then let's see, 33 is not prime, 35 is not prime, 37 is prime, and it'll be here. And then we have 39, and we have 41. Okay, so it looks like it caught up again. But then once we get to here, we have 43, and then we have 47 after that. And then we have 53 over here. And then we have 59 here. And what's going to start happening after this point is this list is going to start growing a bit more than this is. I mean, this one will always kind of keep up with this, but this one's lead will start to, get higher and higher. And that becomes even more apparent if we look at all the primes going up to 100. So one thing we might conclude is that after, let's see, when was the last time they were tied here? Was it at 37? I think it was after 37. After 37, there are more primes with a remainder equal to 3 than a remainder equal to 1. So based on our little work right here, it seems like there's going to be more primes that get a remainder of 3. And you might also ask the question, why are we even considering this at all? What's the point of this? Well, in the subject of number theory, it actually does matter quite a bit whether you have a prime that has a remainder of 3 versus a remainder of 1. It actually is a pretty relevant quantity to have. Okay, now, based on this, we may say that there are going to be more primes with a remainder of 3. And would that be true? I mean, it seems like we have some pretty solid evidence of it here. And the answer is actually no. So it turns out, I wrote down the number here. So it turns out that if you go all the way out to 26,861, eventually this list will catch up to the 3s and then surpass it. So there are more primes with a remainder 1 starting at this point than remainder 3. And it would take a very long time for us to manually write out that many primes. And indeed, in the 1800s, before they had access to computers, they did assume that, or they didn't assume, they thought that perhaps there will always be more of these. It turns out that later on, they were able to show that no, once we hit 26,861, there's going to be more of these. And then you might be like, okay, well, that was a fluke. Then there's just going to be more primes with a remainder of 1. But then once we get to the number 616,841, then the race flips back over to being in favor of the remainders of 3s. And eventually someone was able to show that this flips infinitely many times. So this race kind of keeps going back and forth between which one has more remainders, and it flips infinitely many times. And by writing out the specific examples, we would, unless we were really masochistic and we did this for a very long time, we would not see this behavior at all. So the moral of this story is specific examples don't prove the rule. Sometimes if we go really far or we find a very specific example, it can break the trend that we've seen. So when we're doing mathematical proofs, we can't just list a few examples and call it a day, because for all we know, something like this could end up happening, and it often does. All right, so there are any questions on this concept? All right, well, that's it for the introduction of chapter 4. And then for the next 2 classes, which will be in person, we're going to spend a lot of time learning how to construct and write out very careful proofs. So we don't say that 7 times 13 is 28. So I will see you all in Little Hall 205 tomorrow. We'll go over this, or go over some proofs. Yeah, no problem. If anyone has any questions, you can hang back and ask if you want. Were you able to do the chapter 4 homework after today's lecture? Not really. I mean, you could start it if you want, if you've maybe read the book, but no, I would wait till tomorrow. But remember, the homework due dates are flexible. So you don't have to hand them in on that day. It's just the recommend. So, but I wouldn't try doing chapter 4 until after. David, did you have any questions?